and for having this hearing. There appear to be two major threads in bioengineered products. One of them is low-valued fuels, which will rely importantly on things like a carbon tax, price on carbon emissions. The second one is unique high-valued products. As an example of this, I think in Dr. Carlson's testimony, you were talking about a modified PMMA with better properties than normal plexiglass that might uniquely be able to be produced through biochemical means. And so my questions there is, I guess, first to Dr. Simpson, assuming you have an optimal price on carbon emissions rather than one targeting specific crops, what is the range of carbon, the price on carbon to which the state-of-the-art in biotechnology would allow you to be commercially viable with a simple carbon price alone? How close are you right now?
So right now we are operating commercially in an environment where there is no price on carbon. So we produce fuel ethanol in China. There is no price on carbon in China, and we're able to operate entirely viably. The plant that we constructed has a 3-year payback period.
Well,
so this allows us, because the inputs we're able to leverage are themselves very low cost, our advantage because they are low cost, they are non-commodity, they're found in a single location, they're not food, and they're essentially industry waste with no other value other than to be burned as power. We're able to produce.
Oh, so they're not, for example, just pure carbon dioxide. They have a significant energy content in carbon monoxide or hydrogen.
Exactly.
Similar. Okay,
exactly.
So that those are not going to be available on as wide a scale as carbon dioxide would be, for example.
Carbon dioxide is certainly available in extraordinarily high volumes, but carbon dioxide can also be leveraged in the context of technologies like electrolysis, which would allow you to produce hydrogen from, for example, sustainable power to leverage carbon dioxide. However, I would say that the resources that can be converted into carbon monoxide and hydrogen are broad and widely available.
Do you have an estimate of what fraction of carbon emissions could be, if you could capture 100% of energetically viable carbon emissions?
Certainly.
What
so
fraction?
if we were able to capture, for example, all the emissions from the steel industry, all the emissions from refineries, and convert all available agricultural residues, we estimate that we could produce over 700 billion gallons of fuel annually. To put that into context, the current global production of fuel ethanol sits at around 26 billion gallons. So this would allow us to displace something like 33 to 35% of global transport fuels using emissions or wastes from industry, society, and agriculture.
And so, I guess, Dr. Carlson, can you say a little bit about the outlook for specialty chemicals that are uniquely provided by biochemical means?
I can. It's spectacular. So one thing that I didn't point out during the first part of my testimony is that roughly $100 billion in biochemicals that are already out there in the market, that's somewhere between 1/7 and maybe a quarter of the total chemical sales in the United States. So already biochemicals are a massive contributor to the chemicals industry, and we just don't know it because we don't measure it. I'd really like to have a better understanding of what that number is, because those are chemicals that are, as best I can tell, just already outcompeting petrochemicals on price and performance. And then as we learn to better engineer materials, whether that's concatenating unique unit chemical operations that enzymes can perform naturally to make new chemicals, or as our companies are doing now, to design enzymes that have never existed before, that create chemical operations that have never existed before, to manufacture compounds in biology that have never existed before, but that have been sought for quite some time, the world is going to start to look very different. So the set of chemicals that we can make right now using synthetic chemistry is actually quite small compared to what we'd like to make, and the universe opens up as we learn to make those using biology.
Yeah. And I guess one of the things that's opening that up is the whole CRISPR-Cas9, revolution. And I guess I'd like a shout out to the, tomorrow we're going to have Jennifer Doudna, the inventor or the co-inventor of the CRISPR-Cas9 system, here in Congress for an R&D caucus briefing to staff members. So any staff members interested, it's I think at 10:30 tomorrow, along with the Biophysical Society having that. And if I could just close quickly, the whole issue with human genetic engineering is something that has been, I think we had our best ever attended hearing of the Science Committee when we we had Jennifer here to talk about human genetic engineering. I think it was ironic that the National Academy study, the second one, was the venue at which the Chinese announced that they had genetically engineered a child. So this has gone from sort of fringe speculation to something that exists that we have to deal with. So I guess if I can ask you one question, is there any alternative to very intrusive international regulation to prevent the abuse of things like human genetic engineering or bioweapons?
Genetic engineering for reproductive purposes and bioweapons are two different kind of discussions. But I can just say that there was everybody else on the planet, except for one rogue scientist in China, was abiding by a very carefully constructed moratorium crafted by the national academies of 3 countries. And that moratorium was honored, but not fully understood, and clearly by this man. And it's still, we have yet to see those babies, so it's unclear whether it's how real the story is, but let's just say it is. He was promptly disciplined by, and carefully disciplined by the scientific community of China and the ethical community of China. So it did show that if you violate the moratorium, there will be significant repercussions. And people who gave him advice are also being reviewed very, very carefully. And strong sanctions will be taken, I think, in those cases. And certainly strong academic approbation will be directed to the people who gave him that terrible advice or didn't disclose what he was doing. Is there anything to prevent this? Reproductive uses of CRISPR technology always needs a woman to agree to become pregnant to give birth to a child at tremendous risk. There's no way to do that safely. There's no way to construct a phase 1 clinical trial with safety. And so ethicists have long opposed this until much more safety standards could be demonstrated much more carefully. And that's a long way off. For biotechnology, for weaponry, is a much more sobering discussion. I know Dr. Carlson has spent a lot of time thinking about that. We want scientists to be good. My job as an ethicist is to train them to know that you ought never do harm with your science, and that every gesture of science is a profound moral gesture as well as an interesting scientific gesture. And it's my hope, my fond, optimistic hope, that if you train someone to be moral and ethical and responsible to his or her colleagues as well, they would never think about using their technologies for nefarious purposes. But these are powerful technologies, and they are self-sustaining, and careful consideration has to be put in place in addition to ethics training for the regulation of those technologies.
Yeah. And unfortunately, I think one of the lessons I take away from computer viruses is that everything bad that can be done has been done with computer malware. And the fact that there's a very small footprint for these laboratories now, and shrinking footprint is a cause for concern. And I urge all of my colleagues to have the classified briefing on the technology. And I am past my time, so all right.
We can do it second.
Okay, so we're having a second round?
Yeah.
Great, wonderful. Yield back.
Yeah.